welcome back to this channel. After having the idea how to predict the major product based on the Saytzeff rules, so today we will focus on the mechanism of the alcohol to form alkene, which we try to fulfill the learning objective for D. Outline the mechanism for C1, dehydration of alcohol to alkene. Okay, so when we mention about reaction mechanism, so we need to know what is the mechanism basically refer to. If you still remember in the chapter alkene, we already go through. Basically, this is a process at where you are going to show the bond breaking and also bond formation, and then one step at a time, and then you are going to use the arrow to show the movement of electron. Based on this video, the purpose is we want to show the process of dehydration of alcohol. That means alcohol will remove water to form alkene. Therefore, the type of reaction is elimination, and the type of cleavage is heterolytic cleavage. Means that we are going to use full-headed arrow like this. So basically, in the mechanism, we're going to involve 3 steps. So before we go in each step, let's understand the meaning of the statement here. Protonation. Proton, the symbol for proton can be represented by H+. Of alcohol, maybe we can think of what is the functional group at the alcohol is the hydroxyl group. So means that later you will focus on the hydroxyl group, which consists of 2 lone pair electrons, and then one of the lone pair will attach to the hydrogen later, and left one lone pair with the charge of positive. So step number 2, loss of water to form carbocation. Okay, so basically you will see the structure for this part after the protonation. After protonation, this part is like the water, so we have to remove this part. Okay, after remove this part, and then now step number 3 is Deprotonation. So D has the meaning of remove. Okay, after you remove the water, in step 2, it will form carbocation, and then you have to consider whether rearrangement occur or no. So how you going to know whether the rearrangement is occur? Basically, we look at, is it the carbocation is the tertiary? If yes, then no rearrangement. But if it is primary or secondary carbocation, then you try to check whether it can rearrange to form tertiary carbocation. So after identify the most stable carbocation, then go to next step 3 is remove proton H+. Okay, so in the coming slide, we are going to start with the mechanism for the dehydration of 2-butanol. Okay, step 1, protonation of alcohol. Like just now we say that there is adding, okay, basically we can say is adding H+ at hydroxyl group. Okay, so if you still remember that just now we say that for the mechanism, we focus on the bond breaking and also formation. So because in this step 1, we know that we are going to focus on the hydroxyl group, okay, and also the proton. So if you still remember previously, when we write the mechanism, when we write the equation, we say that dehydration of alcohol need concentrated H2SO4. So this basically is the H2SO4, hydrogen 1, 2, S, 1 oxygen, 3 oxygen. So this basically is the H2SO4. So what will happen, like in the mechanism in alkene, we need to make a story so that we can remember the mechanism easier, and later you can write out easily. Okay, as we know, for the oxygen, always have 2 bonds and 2 lone pair electrons. Okay, so that means in this condition, we have to show the 2 lone pair electron, 1 pair at the top here, and then another 1 pair at the right hand side here. So again, oxygen have 2 lone pair electron, so means that they have more electron. But then now the hydrogen here is the species lack of electron. So maybe you can do the story that the oxygen now have 2 lone pair electron and feel very boring. So they go and look for another kawan. Okay, look for another friend, which is the hydrogen. So because of hydrogen is the species which lack of electron, and oxygen now have 2 lone pair electron. So what happened? So the oxygen will pursue hydrogen become oxygen's friend. So how they pursue the hydrogen? Okay, maybe I say this is the oxygen one, okay, and then this is the hydrogen one. So the oxygen one pursue hydrogen by giving it 2 electrons. So that's why you can see here there is a full-headed arrow. So when the hydrogen one want to break the bond with the oxygen 2, so due to the different electron negativity, oxygen is more electronegative. So both electrons in this bond will not gain by hydrogen, but will only gain by the oxygen. So that's why when the hydrogen follow it, so here you will see from 2 lone pair electron become 1 lone pair electron at the oxygen 1, and another 1 hydrogen is definitely is hydrogen 1. Okay, we don't need to show the numbering here. I just I show this numbering so that you are easier to understand what I refer to. So the H2SO4 is already lost 1 H plus, so that's why the formula will become HXO4 negative. Okay, so this is the product here. So we consider complete for the step 1. Now we go to step 2. It's saying that we lost the water. So when you look at the structure here, which part is similar with the water? Definitely is this part. Okay, so we are going to remove this H2O. So again, in between the bond carbon and oxygen, oxygen is more electronegative than carbon. So that's why this bond will break down heterolytic again, and this time oxygen also will get both electrons when it breaks the bond with the carbon. So after that, then we can see H2O is formed at the back here, and then all the part will remain, only the carbon number 2 will become C plus because lack of electrons. So now we will consider this carbocation ion. So this carbocation ion is bonded to 2 carbon. So we consider that this is secondary carbocation ion. So if you still remember, just now we have to mention, after we form the carbocation ion, we have to check whether rearrangement is happen or no. Okay, so how are we going to know whether rearrangement is happening or no? So our syllabus is quite simple. You just try to shift the positive side to the left and also to the right to check the condition. So if you shift the positive side to the left hand side, that means at the same time you have to shift because rearrangement. That means positive side will shift with hydrogen. So if this case happens, that means here will become CH3 will become CH2 plus, and then CH will become CH2 CH2, CH3. So if you shift the the positive charge with the hydrogen at the left hand side here, you will get primary carbocation ion. How about the right hand side? So if this happens, you will have CH3, CH2, CH plus, and CH3. So in this case, this is the secondary carbocation ion. So now we have three possibilities: secondary, primary, and secondary. So if after rearrangement, this one becomes less stable, will not happen. Okay, so after rearrangement, the class of the carbocation ion is the similar, so we also consider no need undergo rearrangement. So for this question, we are using the example that without rearrangement, so that we can proceed to step 3. Okay, step number 3 is deprotonation. We're going to remove the proton H+. So how the proton will be removed? So we will use the HSO4 negative from the step 1. Don't forget the H2SO4 is playing the role as the catalyst. So catalyst always will form back at the end of the reaction. So now if you still remember in the in the Saytzeff rules, we have mentioned that after we remove the OH, and then we're going to remove one hydrogen next to the carbon cation ion. Okay, next to the carbon with the hydroxyl group, either it's left hand side or right hand side. So we look at the first possibility, the HO4 negative. So among the hydrogen, sulfur, and oxygen, the oxygen has the lone pair electron. Okay, so that's why the arrow is showing from the, maybe you can draw the lone pair electron. So the arrow is from the oxygen to this hydrogen. Okay, it's from this oxygen to the hydrogen. So it means that the oxygen willing to give one pair of electron and share with the hydrogen. So then this hydrogen going to break the bond with the carbon. So in this case, carbon and hydrogen, carbon is more electronegative than hydrogen, because we know hydrogen is the most electropositive atom. So again, this bond will break down, and then carbon will gain the 2 electrons. So after carbon gain the electron, it will share with the carbon next to it, because the neighbor has not enough electron. So that's why the double bond will be formed in between carbon 2 and carbon 3, like here. So beside from the right hand side here, we also can, the HSO4 negative can give the lone pair electron to the carbon, to the hydrogen, which next to the carbocation ion at the left hand side. Okay, so again from HSO4 negative, one lone pair electron from oxygen will give to the hydrogen and share with hydrogen. So again, the carbon is more electronegative, so it will gain the electron and it will share with the carbocation ion over here, which is lack of electron. So the double bond will in between carbon 1 and carbon 2. Okay, so now we already have 2 alkene. So now we need to know which one is the major product based on the Saytzeff rules. Okay, the answer already shown to you. At the top here is the major product, because this carbon, we highlight the carbon-carbon double bond, and then we're able to identify there are 4 groups, 1 group, 2 group, 3 group, and 4 group. Among these 4, there are 2 alkyl group. For this one, they have 1, 2, 3, and 4. However, only have 1 group is alkyl group. So that's why At the top here is the major product. But then don't forget, HSO4 negative, when share the oxygen share one lone pair electron with the hydrogen, then the product, don't forget the product here will be H2SO4. This one also the same thing, H2SO4. Because we are still new here, so that's why we will try to draw all the possibility. But in the exam later, you only need to draw the mechanism for the major product. No need to write the mechanism for the minor product. Okay, let's look at one more example for the mechanism of dehydration of alcohol. In this case, we are going to use 2-methyl-1-butanol. So based on the mechanism here, step 1 mechanism here, we can see at the left hand side here is the structure for 2-methyl-1-butanol. And then at the same time, we also notice that the numbering is number from the right hand side, carbon 1, carbon 2, carbon 3, and carbon 4. So maybe you will ask, why I cannot put the hydroxyl group at the left hand side here? Definitely you can do so, but if you put the OH over here, for example, so later when you want to draw the arrow, it will be from far off the left to the right here. So it's okay, no problem as well. Okay, and just to show you, there are two possibilities. Not necessary every time we start from the left hand side. In the mechanism, normally we will try to put the function, the part at where there is bond breaking or bond formation at the right hand side, so that it will be easier to show the arrow. Okay, so before we continue, we remove the part which is not needed first. Okay, so let's do the story, make the story. Oxygen have extra lone pair electron, so they tend to donate to the hydrogen. So since the hydrogen accept the oxygen one, so it have to break the bond with oxygen 2 heterolytically. So in this case, HSO4 will be produced, and we so-called protonation of alcohol. Means that the hydroxyl group now have extra one hydrogen. So don't forget, now the oxygen from 2 lone pair become 1 lone pair electron, and they will have the positive charge, because compared to 2 lone pair, they now is at the lack of electron. So that's why it's positively charged. Now we go to step 2, formation of carbocation ion by losing water. So that is very obvious. Again, the structure of the water is at the right hand side here. So basically the bond also is break between the carbon and oxygen. So oxygen is more electronegative, so the bond will break heterolytic. So we are going to use full-headed arrow. So when this happens, so this one will become CH2 plus S here. Okay, and here. So and then after form the carbocation ion, so we need to classify. This carbocation ion have 1 bond bonded to the carbon and then 2 bond bonded to hydrogen. So that's why it is primary carbocation ion. As we know, tertiary carbocation ion is the most stable, and then primary is the least stable. So in this case, we have to consider rearrangement. Okay, so rearrangement here, the name for this rearrangement will be known as 1,2 hydride shift. Okay, why we call it 1,2 is because of this carbon and this carbon is next to each other, so it is considered 1,2, just to show that the position is next to each other. And then hydride is referred to hydrogen, shift as we know lah, tukar gantian. Okay, so means that if you look at here, they have shown the arrow, this hydrogen is going to shift to this carbocation ion. So means that the positive charge and the hydrogen changing the places like this. So now the positive charge at here and then the hydrogen is at here. So at this condition now, the carbocation ion have 3 bonds. 1 bond at the left, 1 bond at the right, and 1 bond go to the bottom here. So all the 3 bonds are bonded to the carbon or bonded to the alkyl group. So this carbocation ion is tertiary carbocation ion, which is more stable than primary carbocation ion. So that means in this case, it is different from example just now. This case, we need to undergo rearrangement. Okay, now go to last step, step 3, deprotonation. So we're going to use HSO4 negative. So the lone pair electron from the oxygen now have 3 possibilities. It can remove the hydrogen from the right, the hydrogen at the bottom here, or the hydrogen at the left hand side here. However, you will notice that this one is CH3, this one also CH3. So basically, they are similar. So we only need to remove either one of the hydrogen. So we choose the right hand side here. Okay, so now let's go. Let's say this oxygen go to, okay, since let's say here, you can draw from the bottom and then to the top here. Okay, or you can directly from the top here go to hydrogen. Also no problem, it is free to do so. Only the things that you must remember is the arrow must be come out from the oxygen and pointed to the hydrogen to show that the lone pair electron is from oxygen and then going to share with the hydrogen. Then now the bond between carbon and hydrogen will be break down heterolytic as well, and now this time this electron will form at here. Then this is why you will have the structure CH3 CH2 C double bond CH2 and then you will have one CH3 at here. Okay, this is the first possibility. Okay, so now we try to look at the second possibility. So for the second possibility means that we are going to remove the hydrogen at the left hand side. So for this case, maybe you need to show the bond for this hydrogen. Okay, instead of you doing H2. Okay, because we want to show the bond breaking and bond formation. So again, this lone pair electron from the oxygen, you have to know this is the another HSO4. Only I show you at the same time because I want to show the 2 possibilities. So if, okay, we have 2 methods. One is from the green color one and then another is from the red color one. So if from the red color one, we'll go and share the electron with the hydrogen at the left hand side here. The bond also will break, and then the double bond definitely in this time will form in between with the carbon cation. So if this happens, so the product will be CH3 CH double bond C CH3 and CH3. So now, and then don't forget the HSO4 negative, if you get one hydrogen, will become H2SO4. So now we want to check which one is the major product. So definitely 1 group, 2 group, 3 group, and 4 group. Among these 4, we have 3 alkyl group. 1 group, 2 group, 3 group, and the 4th group also hydrogen. So 2 alkyl group. So this is the major product. So in exam, you no need to show the one with the green color. So you can erase this one, the HSO4 negative need, and then you don't need to show this one because this is the minor product. Okay, so we try to complete. Okay, so this supposedly is the equation. Don't forget here we still have H2SO4. Okay, then like this one here, maybe you need to take note, make sure it is very clear to show that it's full-headed arrow, because like this one looks like full-headed, okay, like this one looks like full-headed and also looks like half-headed. So please make sure you remark it clearly again. Okay, yes. Okay, so that's all for the mechanism of dehydration of alcohol to form alkenes. Okay, I hope with these two examples you have clear image about how to write the mechanism. So in next slide, it's a practice for you to write the mechanism. Okay? Or now, just now we say that you need to have a practice. So please go to the Chem-Friend question number 12, dehydration of 3-methyl butanol with concentrated sulfuric acid. Use a mixture of 3 alkenes. Okay, so in this question, it is very obvious. Let us know there is 3 alkenes. Draw all the structure of the alkene. So draw all the 3 possible alkenes and then think about which one is among these 3, which one is the major product, and then how you determine this major product based on what rule that you use. Okay, and then use to identify the formation of the major product and propose the mechanism of its formation. So here the its formation basically is referred to the major product. So please do a practice and then we will compare your answer with your friends during the tutorial time. Okay, so see you in next video. Please like and share this video with your friends if you found that it is easier for you to understand. Thank you. Bye bye.